Welcome everyone to these lectures on quantum computing and quantum information. So today what we're going to do is discuss a little bit about experimental quantum computing, right? So to do that, what we should first do is ask ourselves, what are the requirements for quantum computing, right? If I want to experimentally implement quantum computing, what are the requirements to do this, right? So this question actually leads us to something called the DiVincenzo criterion, right? When one discusses the experimental implementation of quantum computing, one has to realize that quantum computing is only possible if a stringent list of requirements are met, right? Let's remember for a second that even classical processors have to obey a list of very sophisticated requirements before they can be manufactured, right? In exactly the same way, non-classical processing has to meet an even more stringent list of hardware requirements. These requirements are collected under a name, and this name is the DiVincenzo criterion. It's named after the person who wrote the paper. So let's look at DiVincenzo's list to understand the constraints that are placed on quantum computing and the experimental implementations of quantum computing. Right? DiVincenzo's criterion is a list of 5 primary goals and 2 additional criteria. The primary goals are the following. The first is that DiVincenzo demands that for quantum computing to be possible, there must be a scalable system with well-defined qubits. Right? Now, what this means is that the individual physical qubits underneath must behave well, and when several qubits are put together, this system should behave quite well. Right? So this is the scalability requirement. The second requirement is that the initialization of this system to a simple quantum state must be possible. Before any state preparation is possible, the first step that is often demanded is that we must be able to initialize this quantum system in a given initial state. Right? For example, the state can just be the ground state of let's say a spin quantum computer if it has many spins in it. It's just the ground state of these spins, right? Of the Hamiltonian that describes these spins. The third of these criterion is that many gates must be implementable before a characteristic decoherence time elapses. Right? This is a slightly elaborate requirement, and so we will look at this requirement separately. Moving on, the fourth requirement is that a universal set of gates should be possible. This is, of course, very easy to understand. 1 qubit and 2 qubit gates, which compose the universal set of gates, must be implementable on our quantum computer. Right? The fifth requirement is that we must have qubit-specific measurements. Right? So imagine that you have a quantum computer that has, let's say, 100 qubits in it, and you encode the information in the first 100 qubits, and then you perform the quantum computation going forward. Then what one must demand is that wherever the answer is, or whatever part of this 100 qubit chain that you want to measure out to get the answer, such measurements must be possible in general. Right? Remember that we are discussing here the circuit model of quantum computing, but if you consider alternative models of quantum computing, such as measurement-based quantum computing or topological quantum computing, the requirements look fairly similar, but with small differences. So, for instance, measurement-based quantum computing would demand that the initial state of the system be a cluster state, right? But once you've prepared the state, the requirements that measurement-based quantum computing has to perform universal quantum computing are somewhat less stringent. Likewise, topological quantum computing comes with its own set of requirements. There are 2 additional criterion that are also part of the DiVincenzo list. The first of these is interconvertibility between stationary qubits and flying qubits. Right? If you try and imagine what this sentence means, it's simply the requirement that if my quantum computer is composed of a large number of qubits, like I just described, then you can think of the computer as having subsystems. Right? So a subsystem over here which does something, and then maybe I want to pass this information on to the subsystem over there for it to do something else. And this passing of quantum information must both be possible. This is the demand that you have interconvertibility between stationary and flying qubits. And the second demand, the last demand, is basically that such a transmission of quantum information be faithful, right? So this is the DiVincenzo list. So to understand the DiVincenzo list, what is left for us to understand is requirement number 3, which is basically the demand that the decoherence times be much larger than the gate times, right? So to understand that, let's try and understand a little bit about decoherence now, right? To understand decoherence, here is a classical analogy. So consider a simple pendulum that is suspended at some point, and let us assume that we would like to track its dynamics. Let's say the x coordinate is what we're interested in. Then what we would like to do is model basically what happens to this simple pendulum, keeping in mind that this simple pendulum is suspended in air. What that means is that not only is this simple pendulum's oscillation dictated by its own motion, but there are all of these collisions with the with these atoms that I've represented here as these red points. These atoms collide and carry energy and momentum away from the pendulum. So what we would like is to describe the dynamics of the pendulum, and to do that there is the hard way and the easy way. The hard way is to actually write out Newton's equations for every one of these particles here, the pendulum and all of the red particles that represent the air molecules, and then solve this coupled set of differential equations and then try and arrive at what happens to just our pendulum, right? On the other hand, we've developed a much better way of describing what happens to this pendulum in terms of a damping parameter, right? So when we write the differential equation for a damped harmonic oscillator or a damped pendulum, what we are describing is the effect that all of these molecules have on this pendulum, and hence we see a solution that looks like the one that I've plotted on the right. So the position as a function of time simply oscillates as you would expect a pendulum to do, but also fades away, which represents the fact that energy and momentum are getting carried away into the environment, right? Such a dynamics is called damped. But the most important thing to consider here is the fact that we've done two things. One is that we've identified to begin with what the relevant degrees of freedom are for our pendulum, right? In this case, they are the x coordinate is what we're interested in, right? And the second thing that we've identified is that there is an effective model for the environmental interactions, in this case air molecules colliding, in terms of a damping rate, right? And once we put both of these things together, we get a very simple differential equation, which is the damped harmonic oscillator, the solution to which is the effective dynamics on the subsystem, on the system, without considering the environment, right? So this is the basic plan that we would like to follow also in the quantum regime, right? Damping, the quantum analog of damping also follows an exactly the same story. So here what we have is we have a qubit of our interest, which is this blue qubit, and there are several red qubits around it, which represent an environment. For instance, an electron sitting in a bath where there are nuclei around, right? And what we want to do is just describe the effective dynamics of the system, right? So the first thing to do is to identify how to describe the system, and this is of course described by the density matrix rho of t, right? And then to discuss what happens to the environment, we need a good model, an effective model of what is happening in the environment, right? Such a model is given by considering the following. So we start with the density matrix of the system at the initial time, the environmental density matrix at the initial time, and a joint unitary interaction which is composed of a system Hamiltonian, environmental Hamiltonian, and a coupling, right? And then what we do is we basically evolve this joint system for a while, and we trace out the environment because we don't wish to know the dynamics of the environment, right? Once we do that, under certain other assumptions which are simple to state, one obtains a set of equations called the Lindblad equations. The Lindblad equations can be described thusly. The time derivative of the density matrix has the usual Hamiltonian part. This is just Schrodinger's equation in the density matrix picture. And then there are a set of terms that accompany it, right? These terms are written in terms of these damping rates gamma k of t and corresponding operators a k of t. What I will show you now are several examples of these damping rates and these operators to develop some intuition about this model, right? What I would like to emphasize is we've done the exact same thing here that we did previously for the classical damped harmonic oscillator, right? Which is we have the system dynamics being described in terms of some operators that act only on the system. The environment is nowhere here, right? It appears indirectly through these operators ak and gamma k, right? Let me point out that other models of so-called open quantum system dynamics exist, and here is a standard reference, right? So here is the first example. This is called phase damping, and phase damping basically involves one parameter gamma, and the operator ak is the sigma 3 operator. I've written down the Pauli matrices just to remind us. And the equation can be solved easily. It can first be simplified in terms of the rotating frame. What the rotating frame means is to simply go into a frame of reference that's rotating with this Hamiltonian h of t, and then we get a density matrix rho tilde of t. And in terms of rho tilde of t, we can write the equation of motion very easily as d rho tilde of t by dt is gamma sigma 3 rho sigma 3 minus rho, right? This equation can be solved by simply noticing what happens to a density matrix rho in terms of the three block parameters R1, R2, and R3. So what happens to this density matrix is that the R3 parameters are left unchanged, but the R1 and R2 parameters change signs, right? And hence what we can see if we solve the differential equation is the following. The R3 of t simply remains at its initial value, and what this represents physically is it represents the fact that the populations don't change, right? So let me go back and point out that the populations of the density matrix are along the diagonal 1 plus R3, 1 minus R3. Whereas R1 and R2, which represent the coherence of this qubit, are along the off diagonals, and the off diagonals basically start decaying very, very quickly and rather exponentially with this rate gamma, right? So now we can understand what this criterion T decoherence much larger than T gate actually means. What it means is the following. So let us imagine that we have a quantum computation that proceeds thusly. So there are a bunch of gates that we would like to apply, and in this cartoon that I've drawn below, imagine that the single qubit gates are given by the small bump, whereas several 2 qubit gates are given by the longer bumps, right, the taller bumps. Then this quantum computation, which is which we would like to act on the system, if this represents the real time that it takes, it's plotted on the same axis here, t. If this represents the real time that it takes to execute each of these gates, imagine what happens. So at the beginning, this gate is acting on a fully coherent quantum system, and so the quantum computation proceeds accordingly. But by the time you come somewhere here, right, by the time this much time elapses, this computer is no longer effective because it is suffering from the decoherence that is induced by the environment, right? And by the time we come basically halfway through the quantum computation that we would like to perform, the coherence in the off diagonal sense, the coherence of this quantum computer is completely gone. Now, what that means is that this computation cannot proceed at all, and the answers that we get are at best unreliable, and more often than not, they're just not available at all, right? So this is in fact the problem that De Vincenzo is trying to solve by demanding that T decoherence be much larger than T gate. T decoherence in this case is simply the inverse of gamma, 1 over gamma, because R1 decays as R1 e to the minus T over T decoherence. If I write gamma as 1 over T decoherence, right? So that's the entire point of criterion 3 in the list. So let me move on by showing you one more example of decoherence. So this is spontaneous emission, where instead of sigma 3 rho sigma 3, we have two operators sigma minus and sigma plus, and this differential equation can also be solved. And what one notices is that the again in terms of the R1, R2, R3 parameters of the density matrix, both the off diagonal terms decay exponentially, whereas the diagonal terms basically settle down in the ground state, right? So they settle down in a way where the quantum system settles down in the ground state, which is exactly what spontaneous emission does. So if you start a bunch of qubits with a lot of coherence, the system basically loses all its coherence, and the qubits all end up in their ground state, again rendering this quantum system useless to do quantum computing, right? So this is the entire point of decoherence, and the point that is made in in demand 3 of the De Vincenzo list. De Vincenzo is arguing that we must fight this decoherence to be able to do quantum computing effectively. So let me just take us quickly to a take-home message, which is the following, which is that we must control decoherence for experimental quantum computing, right? What we saw quickly was one model of decoherence in terms of what are called Lindblad equations, right? The methods to control can be rather elaborate, right? They can start from very simple methods like simply engineering a better qubit, to isolating this qubit from all its environment, right? To cooling the qubit. These are all rather simpler measures. There are more advanced measures such as the spin echo technique, dynamical decoupling, error correction, and decoherence-free subspaces, right? And I'll introduce some of these to you. To introduce them, what I must now tell you is what the popular implementations of quantum computing are. And so here are some experimental implementations of quantum computing, the framework or the architecture over which quantum computing is built. The first of these is nuclear magnetic resonance, which we will consider rather elaborately. The next experimental implementation is ion trap quantum computing, which is going to be the topic of the next lecture. The third is photonics or linear optical quantum computing. These are slightly separate, but this is a rather popular quantum computing architecture as well. The last is superconducting qubits. I'd like to point out for anyone who knows what the D-wave machine is, that the D-wave machine is in fact built on superconducting qubits. So let's look at NMR quantum computing. So NMR quantum computing is built on nuclear spins, which are qubits. To discuss them, let me describe to you the block sphere representation, right? The block sphere representation is simply a representation of a pure state in terms of two variables, theta and phi, right? And these theta and phi describe points on a unit sphere, right? So this block sphere or Poincare sphere, as it's sometimes called in optics. So the block sphere representation is used extensively in nuclear magnetic resonance, and we too will make use of it in our discussion today. Let me point out that nuclear magnetic resonance is performed on several nuclear spins, but some of the most popular choices are the hydrogen atom and chlorine, right? To discuss decoherence in nuclear magnetic resonance, we will again appeal to this block sphere representation that I have just discussed. So the decoherence model that nuclear spins suffer from can be described rather simply. So what happens in nuclear magnetic resonance is that typically it's either the nuclear spins are either in solid state or in liquid state. So let's consider the case where the nuclear spins are part of molecules, and these molecules are part of a liquid. They're suspended in a liquid. Each nuclear spin suffers from a slightly different environment. As a consequence, when the nuclear spin precesses, each nuclear spin precesses by a slightly different amount. So what this produces is this figure that I have illustrated. So when imagining that the precession is happening in some axis, what happens is that if the nuclear spins are all initially lined up with this central spin, because their environments are different, these nuclear spins basically fan out like this. So when we average over several nuclear spins, which is the signal that is received in NMR, we see that the signal is decohered because of the averaging process, right? So how does one fight this? One fights this again by looking at the block sphere for inspiration, and this technique is actually called the spin echo technique. Okay. So imagine that a nuclear spin is pointed along the north pole. The spin echo technique starts by rotating this nuclear spin along the minus y-axis, right? And then what happens is that as a consequence, the nuclear spins, as a consequence of their local environmental differences, the nuclear spins start fanning out. Once they fan out, what one does is applies a pi pulse, which rotates the orientation of all of these nuclear spins from the minus y to the plus y axis in this diagram. Now, because the nuclear the environments of the nuclear spins are still rotating them in the same direction, what happens is that all the nuclear spins start accumulating and recohere. And once the spins have recohered, there is another pi over 2 pulse that's applied to bring it back to the North Pole. So such a technique actually preserves coherence over the time scale that it takes for us to do these 4 operations. And hence the spin echo technique is able to keep coherence over a much longer time by actually performing these 4 steps and recohering the spins at a later time. Dynamical decoupling, which I mentioned briefly, is a general technique related to spin echo. So let me describe briefly the experimental techniques that are involved in NMR. The experimental setup of NMR involves a compound such as chloroform suspended in a liquid, which I've diagrammatically represented here as this box, between 2 fields. One of them is a static magnetic field and the other of which is a radio frequency field. There are 2 common types of NMR, liquid and solid state NMR. Let me describe how single qubit gates are implemented in nuclear magnetic resonance. The Hamiltonian is composed of 2 terms, and this is a direct consequence of our choice of radio frequency and static field. So the first term relates to the static field, and it produces a Hamiltonian which is minus h bar omega naught Iz. Here the I matrices are simply half of the sigma matrices. And the second term basically is a radio frequency times Ix, right? Like before, we can go to a rotating frame with respect to the unity e to the minus I h bar omega naught Iz times t. And if we insist that the density matrix in the rotating frame have the same form as the Liouville equation, which is I h bar rho dot is equal to h rho, then what we come up with is a final Hamiltonian in the rotating frame, which basically looks like an off diagonal e to the minus I phi and e to the plus I phi, right? So this Hamiltonian can be written as a linear combination of the Ix and Iy matrices, right, which are again just the sigma x and the sigma y matrices up to a half, right? Now we understand how any single qubit gate is possible, because if you choose different values of omega 1 and phi, then what that does is it changes the Hamiltonian, and you are able to implement either the Ix part or the Iy part or some linear combination of Ix and Iy. As we fully know, by using the Euler angle rotation, we can implement any series of gates so long as we have sigma x and sigma y matrices, right? So this is the way in which all single qubit gates are performed, by simply choosing various values of omega 1 and phi, right? So let's now describe briefly how 2 qubit gates function in nuclear magnetic resonance. For 2 qubit gates to be implementable, what one needs is some sort of interaction between nuclear spins. So for example, in NMR, the Heisenberg type interaction is quite common between neighboring spins. So this Hamiltonian is given by Ix tensor product Ix plus Iy tensor product Iy and Iz tensor product Iz, right? And the coupling ratios is the quantity J, right? This is the coupling J. There are 3 terms in the 2 qubit Hamiltonian, and they refer to H naught, which basically is the bare sigma z. It's just a static field sigma z. HRF1, which represents an RF field on the first qubit, and HRF2, which represents an RF field on the second qubit, right? And I've written what HRF1 and HRF2 are here, right? Note that H naught also has this interaction Hamiltonian, which is the Heisenberg type coupling between them, right? So we have several operators here of the form Ix tensor Ix, Iy tensor Iy, Iz tensor Iz. We also have Iz tensor identity, and the radio frequency fields bring with them Ix tensor identity and identity tensor Ix, right? So by using suitable commutators between these operators, what we can do is implement all 16 operators of the 2 qubit algebra, right? There are 4 operators relevant to the first qubit, which are the identity matrix, the poly sigma x, sigma y, sigma z. And there are 4 operators that are relevant to the second qubit, which are again the identity operator, poly sigma x, sigma y, and sigma z, right? So there are 16 operators in total. And again, by simply choosing different values of the radio frequencies and the static fields, we can manipulate and engineer an effective Hamiltonian that basically is any one of these operators or any linear combination of these operators, right? So this is exactly how 2-qubit operations follow in NMR. So again, technically the way to do it is to move to a rotating frame with respect to the bare Hamiltonian. And then we have the Hamiltonian in the rotating frame, so it has this tilde, which is given by Iz tensor Iz, and then there are several terms which now have Ix, Iy, Ix, and Iy. So we can generate all 2-qubit gates by taking H tilde and simply applying it over and over again, but by choosing different values of J, omega 1 and omega 2, phi 1 and phi 2, right? So this is the way in which 2-qubit gates actually proceed in nuclear magnetic resonance. So to summarize, what we discussed today were the De Vincenzo's criterion, which are the crucial criterion for experimental quantum computing. We also understood the origin of decoherence. We actually considered a model of decoherence and studied what decoherence does to qubits and how it is detrimental to the quantum computing process. As an example, we considered nuclear magnetic resonance, and we discussed spin echo as a way to mitigate the decoherence process. Finally, we looked at implementing single qubit and 2-qubit gates in nuclear magnetic resonance. In next lecture, we will discuss why the NMR qubit is not a particularly well-suited qubit, and we will discuss an alternative qubit, which is the ion trap qubit. We will discuss how to trap ions and how to cool them and how to perform various gate operations on them. And this will be a much more viable architecture for implementing quantum computing. Thank you.